Hello, welcome again. We are solving mechanical engineering paper 2 of year 2025 of civil services mains exam. Question number 3B we are solving, and we have solved up to that calculate the mass flow rate of air in the previous video. So now we'll solve the rest part of it. So I will read the question again. A centrifugal compressor is to be designed for an industrial application handling air. The inlet stagnation conditions are P0 is equal to 1.1 bar, P01 equal to 295 Kelvin. The air enters the eye of the impeller axially without any pivot. The axial velocity uniform throughout the eye and is equal to 143 meter per second. The eye tip and the root diameters are 0.3 meter and 0.15 meter respectively. Calculate the mass flow rate of air. There up to that we have solved. So now the rest part is the overall diameter of the impeller is 0.5 meters. The power input factor is 1.054 and the slip factor is 0.9. The rotational speed of the compressor is 290 revolution per second. The isentropic efficiency of the compressor based on total head is 0.78. The radial velocity of the impeller tip is 143 meter per second. Assume that half of the total losses occur in the impeller. Determine the pressure ratio and the power required to drive the compressor. Also determine the axial depth of the impeller channel at the periphery of the impeller. Draw a TS diagram showing the variation of both static and stagnation pressure and temperatures in the impeller and the diffuser. For air, gamma is equal to 1.4 and Cp is equal to 1.005. So we have data from the previous video that P01 is 1 bar, P01 is 295 Kelvin and Ca1 is 143, and we have calculated this P1 and rho 1, then mass flow rate, we have calculated this P1, rho 1 and mass flow rate. Okay. So now next we will calculate the impeller tip speed. So impeller diameter is 0.5 meter and RPS revolution per second is 290. So impeller tip speed comes as 445.5 meter per second. Okay. So now we have one relationship between the stagnation temperature rise and the work input. So that is so final stagnation temperature is T03 and initial is T01 that we have studied in the previous video. So that is your heat energy or total energy rise, and that is given by work input, that is psi sigma UC. Psi is your power input factor and this sigma is slip factor. So this is work done, and this work done has caused stagnation temperature rise. So T03 is the final stagnation temperature and T01 is given, that is 295, and U we have calculated. Putting these values we can find out T03, that is 488.4888 Kelvin. So now this is the actual stagnation temperature or final condition. So in the previous video we have also studied that there is if the isentropic process would have been occurred, then the T03 dash would have been the outlet stagnation temperature. So as isentropic efficiency is given, so this T03 dash can be calculated. So T03 minus T01, this is the actual, and this T03 dash minus T01 is the ideal divided by isentropic efficiency. We can calculate T03 dash because we have T01, we have this distance, so T03 dash is your 445.54 Kelvin. Okay. So now because this is the temperature if the isentropic process would have been occurred, we have this T03. Okay, sorry, we have this T03 dash now and we have T01. So we can apply now isentropic process, isentropic relation. So we can calculate P03 by P01. So that is the actual pressure rise 4.23. This is the isentropic relation. So this is the answer to second question. Now we have the radial velocity at outlet as 143 meter per second. So that is given. And CW2 we can calculate, that is sigma u. Sigma is your slip vector and u is your speed. So that is 400 times. So this is the one component of velocity, this is the radial component of velocity. From this we can calculate c2 square because both are perpendicular to each other. So this is your CW2, this is your C2, and from this CR2, this is from this we calculate C2. So after calculating this C2, C2 square, we can divide it by 2CP. Okay. So our purpose is to calculate the static temperature at the impeller outlet or diffuser window. Okay. And we have this T03, and T03 is equal to T02. Okay, we have calculated the stabilization temperature T03, and now we will calculate this C2 square by 2CP, that will come out as 93.8. and from this diagram we can see that this is the C2 square by 2CP and this is your T02 or T03, and if we subtract this quantity from T03 we can calculate T2. Okay. And we have calculated if we have calculated this T2 and if we have calculated T2, we can find out density. So now this is the way to calculate T2. Now we need P2 also. So another condition is given, that is the half of the losses occur in the impeller. So as isentropic efficiency is given as 0.78, so losses are 1 minus 0.78. These are total losses. Half is occurring in the impeller, so the losses occurring in the impeller is 0.11. So efficiency of the impeller part is 1 minus 0.11 or 1 minus losses, that is 1. Okay, now we have this T02, that is equal to T03, T01 and this T01 and isentropic efficiency of the impeller part. Same way we can calculate T02 dash. This is the temperature if the isentropic process would have been occurred in the impeller. So that would come out as 466.77. Okay, now we can apply the isentropic relationship, because this is the isentropic achieved stabilization temperature. So from this we can calculate T02 by T01. So this comes out as 1.582 ratio 3.5. And static temperature, as I have mentioned, can be calculated by subtracting C2 square by 2CP from T02 or T02. So that will come out as 394.2 Kelvin. So now P2 by P02 can also be calculated, because now we have T2 and we have this T1 also, T01 also. Okay, so this is your T01 and this is your P2. So now P2 by P01 is P02 is known, P02 by P01 is known. So from this we can calculate P2 by P01. Okay, so this will come out as 2.35. Now we have P01, so we can calculate P2. So from P2 on, from T2 we can calculate ρ2. So ρ2 will come out as 2.28 kilogram per meter cube, and we have the mass flow rate that we have calculated in the previous section, that is 9.01. So the area required at the impeller will be mass flow rate divided by rho by velocity. Okay, so that will come out as 2.0276 meters, and the depth of impeller will be pi into d into divided by pi d, area by pi d, because area is pi d into depth, d is diameter, and suppose dt is depth, so that this will be the depth. So answer is 1.76 centimeter.